Good afternoon, everyone. I would like to welcome you all to the second NISC online workshop entitled Two-Port Fractional Order Oscillators and Filters Suitable for Tissue Modeling. I am Lubna Ahmed Saeed, Associate Professor at NISC Research Center, Nile University, and I'm EAS co-chair. I will be your host for tonight's session. Let me first give you a brief about our workshop. This workshop is a part of a series of workshops hosted by NISC Research Center and NU Research Office as a part of our vision to contribute to society by disseminating our funded project results. We are actually going to give you a brief of the outcomes of our latest almost finished project funded by Science, Technology and Innovation Funding Authority, STIFA. I have today the project BI and the project co-BI. So let's welcome our guest speaker of today's workshop, Professor Ahmed Radwan, the project BI. Welcome, Professor Ahmed.
Welcome, Dr. Lubna. Thank you.
And Professor Ahmed Madian, the project co-BI. Welcome, Professor Madian.
Thank you, Dr. Lubna, for the introduction.
I'm going to give you a quick introduction about the two professors. Dr. Radwan is our Vice President of Research at Nile University. He's also Professor in Engineering, Mathematics and Physics Department at Cairo University. He is a member of the National Committee of Mathematics, and he's also a member of the Applied Science Research Council, a specialized scientific council at the Academy of Science, Research and Technology, ESRT. He was also a former member of EAS. Dr. Radwan actually on the top authors worldwide for the two research tracks, capacitors, network circuits, fractional order capacitors, and KS series chaotic systems, multi-scroll chaotic, and this is according to SciVal database. Also, now I'm going to give a brief introduction about Dr. Ahmed Madian, our co-host. Dr. Ahmed Madian is our NISC director. He's also a professor of electronic systems. He's a senior member IEEE. He's IEEE Egypt section secretary. He's also IEEE CAS Egypt technical chapter chair and founder, IEEE RAS Egypt technical chapter vice chair and co-founder. He's also a member of the National Committee for Radio Sciences, ASRT, and he is the director of he's also a director of microelectronic system design program at Nile University. Welcome both of you. First, Dr. Radwan, the question is, we would like to ask you about the project general aims, just a brief introduction to the audience about the concept of the project we are trying to disseminate its output will be wonderful.
Thank you, Dr. Lubna, for this introduction. Actually, I would like to thank the STDF for supporting this project. The title of this project is multidisciplinary between, it is a multidisciplinary project between basic sciences and engineering sciences, electronics and engineering, as well as agriculture. The title is Two-Port Fractional Order Oscillators and Filters Suitable for Tissue Modeling. It is an interdisciplinary between mathematical fundamentals of fractional calculus, different optimization techniques, the concepts of two-port networks, oscillators, filters, bioimpedance, and chaotic systems. We did a very good work, and we will try to discuss the objectives and the outcomes of this project during this session, inshallah. Thank you.
Inshallah. Thank you, Dr. Radwan, for this quick introduction. And actually, you did the categorization into points, and it was really wonderful. I see actually a lot of concepts mentioned here. It is an interdisciplinary project. So let's try to simplify the concept to the general audience. I will take the first concept. Dr. Madian, Dr. Radwan just mentioned two-port network analysis. Can you please explain to us its benefit and applications from the circuit point of view?
So thank you, Dr. Lubna, for the introduction. Thank you, Dr. Radwan, for summarizing the benefits of the project. Actually, the concept of two-port network is one of the concepts, I would say that's one of the main concepts that exist in the circuit theory. Most of the circuit theory is already trying always to get outside to the global view instead of working in a small specialized things. It's like when we are looking for a system, we could look to the system in the level of transistors, or could look for the system in the level of resistors, or we could look for the system on the higher level as a closed black box that are doing a certain function. So working with the two-port network is one of the methodologies that already extract the relation between the output and the input, what is inside that already realize this relation. So we are in this project, we are trying to generalize the concept of the two-port network, so we could make or we could determine the kind of relation between the output and the input, and they try to realize this in a different in a different realization techniques and systems that already suitable for the main target of the project, which could be defined as modeling. Okay, so by means of modeling, we have a lot of modeling systems that already existing, modeling techniques that already existing. Actually, also the modeling has a lot of orders. I could say it could be differentiated between integer order and fractional order. Fractional order modeling maybe give us more advantages that already, I think one of the, I couldn't talk in such a kind of topic while Dr. Radwan is existing. He's one of the top ranked persons in this field. So I think maybe fractional order two-port network is one of the main concepts that we are trying to use it inside this project. Okay.
Thank you, Dr. Madian. Okay, Dr. Radwan, fractional. People are already suffering from calculus. So Dr. Madian was mentioning fractional order, so I believe he is talking about fractional calculus. So this is not an easy area of research. I think is in a matter of complexity and application. Can you make our audience interested in working on fractional calculus applications?
Thank you, Dr. Madian. Actually, fractional calculus started more than 3 centuries ago. Okay, between L'Hopital and Leibniz, and in the same time for the classical calculus. But after 1960, there are several approximations of the fractional calculus operators that enable many researchers to discuss different applications and make a realization for the fractional order elements. The fractional calculus is a generalized derivative and the generalized integral, which means that we can get the 0.5 derivative, 0.3 integral. It's a generalized calculus. It gives us the smooth transition between the function and the derivatives, the smooth transition between the function and the integral. It's give us the beauty between and the smooth transition, as I said, the beauty between the function and the dynamics. It's a dynamics. Okay, there are many applications for the fractional calculus in physics, in control, in signal processing, in robotics, in bioengineering, electrical engineering, mechanical engineering, chaos, electromagnetics. Actually, the number of researchers during the last 10 years increased exponentially, okay, and in different applications, and especially in Egypt. I remember very well when in 2005, the number of professors who are working in fractional calculus, like maybe 2, 3 in Egypt. Now I think there are maybe hundreds of professors and their students working in this field in Egypt. The fractional calculus is very important, and we did very good work actually previously in the literature survey of oscillators and filters. And the objective of this project and the relation between the fractional calculus and this project it is very strong actually, because we did a literature survey on the two-port network in the fractional order domain for many applications of oscillators and filters. We did a literature survey for the tissue modeling in agriculture, biomedical applications. We discussed the realization and different realization of fractional order elements using discrete elements and different other techniques with like sensitivity analysis. We discussed the optimization of the fractional order filters and bioimpedance. It's lots of ideas that have been discussed during this project. And actually, we are lucky to have a very good group in NESC to work on this project and to implement all these ideas. So this project actually, it is interdisciplinary between fractional order circuit theory that cover, as I said, chaotic systems, bioimpedance, oscillators, filters, two-port network, and especially the tissue modeling, which is very important in our daily life, and how this is very important to measure the disease and the fruits, vegetables, which match the big project in Europe, which try to digitize the fruits and vegetables in our life. Thank you very much.
Thank you, Dr. Radwan. Tissue modeling, it's interesting. Dr. Madian, studying tissues somehow is a biology-related subject. So you are all engineers. So how could it be an engineering topic? Can you please explain it for us, how the biology topics is now being addressed by an engineer?
So actually, it's a good point. Thank you, Dr. Radwan, for describing that in the fractional part. One of the main points that already most of the humans from all time are trying to describe is how to describe the behavior of the organs, how to describe the behavior of the human. And this is one of the main problems that you that already make a problem or maybe implement it. So I would say I am already preparing something here that already is ready. If you allow for me to share this, just to get the main concept behind the tissue modeling. Okay, one of the categories that already is being used, actually a tissue model is an old topic that already has been existing for a long time, as I said. So the main point, how to model that, okay? In engineering, we didn't know the tissue itself, but always we have, I am an electrical engineer and coming from a background of electronics. So all what I know is current voltage relations between different elements. So some of engineers that already are working to get solutions and to get some kind of biomedical devices to be used for operation and so on, or to be used also to help a human for investigating the different conditions, always depend on this kind of modeling. If you look here, it's some kind of electrical cell electrical modeling. This is, if you look to the left side where this point is here, is representing the tissue of, this is just a model of fruit, okay? We are trying to represent the different relation between the structure or architecture levels of the tissue of the fruits with an equivalent relation that already, as I said before, we are looking for the two-port network and two-port element modeling. We are looking for the system as a black box. So we didn't know what is inside, but we know the relation between the input and the output. So extracting the relation between the input and the output for the cell, I could model it with any other equivalent systems that already determine or that already equivalent the relation between the input and the output. And this is what the tissue modeling is trying to do. We are trying to build models for different tissue types, which represent the different relation between the different layers inside the tissue itself. So a lot of models that has been described. Actually, the most famous model, as Dr. Radwan has mentioned now, is bioimpedance model. which actually most of us could see this example if you are trying to weight yourself and know how the percentage of water, percentage of muscles, percentage of fats in your body. So you just go to get a small scale and just stand on it, or just hold it in your hand, and it will make some sort of analysis that will print a percentage of the different types or the different component of your side, of your body. How this could be described? It could be described through modeling. We are trying to model your human body with an equivalent circuit that represents a different relation between the waters inside your body, the fats inside your body, the tissues examples inside your body. So, and we're trying to describe each one with an equivalent resistance and the capacitances. And this equivalent resistance and the capacitance is already translated into a percentage, which describe the relation between the different points. Actually, a lot of models has been implemented or has been already defined from a long time, that already trying to define different relation inside the fruits, inside the animals, inside the human itself. But not all the models is applicable for all conditions. It means I couldn't use such a model in all tissue types. I have to describe for each model the equivalent tissue type that already could describe the relation. In kind of tissue modeling, we're trying to generalize this model instead of, as I said, it's some kind of measurement. So to verify the model, we have to measure the tissue and try to build from the measurement some sort of mathematical models that we could describe the relation between the input and the output, and then we could realize this. And this could be done through some kind of measuring for the voltage and current. As you see, you may know or not, but I will say that at low frequency, if we're applying a low frequency in a small tissue part, current doesn't pass through the cells itself. It passes through it, okay? Like this case, like case A, it doesn't penetrate the cell, it goes through the cells. But increasing the frequency, the current start to pass through the tissue. And this is how the CT cameras and the other models of different biomedical devices taking CT images for different organs and different levels. So using this property, we could verify how to measure the different tissues for some kind of vegetables or for humans using different types of electrodes. A lot of devices has been implemented under this model, okay? So this model has already helped to implement different models that could already get a result of this modeling to verify if the model is applicable or not. Okay, and as I said, we need both the low frequency range and the high frequency range. So a lot of devices doesn't cover both of those ranges, and actually most of the devices that has been implemented already have a very high, a very high cost. So we are trying in this project to realize the different model techniques for different tissues using the concept of two-port, and trying to apply which of the models that has been implemented. As you see, there's a lot of models that has been already realized based on the categories. I don't want to go into the details because maybe the time doesn't fit with us, but here it's a kind of spectroscopy that already implemented. This is one of the accurate techniques that could be used to realize the bioimpedance, but if you have enough money to get something like that, it would be good, but it would not be portable. And this is one of the main problems, that most of these devices need a special setup inside the lab. So this concept has pushed most of the, actually push us in NISC, and actually Dr. Radwan, one of the leaders in this point, okay, to realize a different devices that could help us to make it portable, and in the same time, it could get us a measurement that could give us the bioimpedance model. And we built such a small prototype in a different project. Actually, this project, it was a processor for this one, which is could be funded by JSOR also. ASRT actually is one of the big supporter for our research. But the main problem is one of the tissue modeling applications that already has been raised lately. It's one of the problem is how to deal with the cancers. Okay, dealing with the cancer is one of the main problems. And actually, we have a cooperation with Professor Ahmed Al-Wakil from Sharjah University, and he's one of the adjunct professors inside NESC, and he has already a high contribution in this field. It's one of the main problems, how to the behavior of the cells that already give us the result of having a cancer. It's one of the problems that we need to understand it. So we need to get out of the cell itself and try to make some kind of two-port modeling for this application. And this two-port network try to study the behavior. Actually, some of the people that are already trying to study this behavior, some kind of, they already has going to the chaos theory to try to understand how these cells behavior is already going on, okay? And I think it's one of the main points that already has been covered during our work here in NISC Center, okay? Yeah, maybe this is, I hope that I already have answered your question about tissue modeling.
Thank you, Professor Ahmed, for this very wonderful introduction about the tissue modeling. But interesting, you mentioned chaos theory. So I would like to ask you, is this the movie by Jason Statham or it's something else?
It's some kind, some of people already is, actually, by the way, having a lot of movies that already describing this relation is very good. But actually, most of the movies already concentrate not on the concept, but it try to use this function inside their target for the audience, okay? But I think the case series that we are talking about is a little bit different. Maybe, I don't know, but also I say that Dr. Radwan also is one of the leaders in this position, so I couldn't talk while he's here. So I think
according to Saival, yes, he is one of the leaders of this.
Yeah, so I couldn't introduce such a kind of relation, and I think I will leave the floor for Dr. Radwan to represent this part.
So Dr. Ahmed, of course, I'm not going to ask you about Jason Statham movie. I'm sure you didn't see it. So, okay. So I would kindly ask you to explain to the normal audience what is chaos and what is chaos theory, and how the fractional calculus enrich the chaos theory, and what are the real life applications for chaos and chaotic systems and stuff like that.
Thank you, Dr. Madian, Dr. Lubna. Let me share the screen. Okay. First. Okay. The definition, chaotic systems actually is very important, and there are many applications that are working and use the chaotic systems. The definition of chaos actually is a deterministic behavior, okay, and it has actually random-like behavior at the same time. So it is deterministic equations, and its behavior like random, like noise, but it's not noise, okay? It is very sensitive to initial condition, and there are many applications that are using the chaotic system, like pseudo-random number generators, like encryption, like modeling in financial companies, cryptography, and synchronization, and lots of applications that are using the chaos. If we see this figure shows how small change in the initial condition can make big difference in time. So as we see back here, they are almost the same in the beginning. A small difference, it's like 10 to epsilon in the beginning, make big difference in the time as time increase. This is what we said, sensitive to initial condition. And actually there are many applications that are using this in our life. Okay, if we are talking about the financial assets or the weather, can we predict the accurate the weather? Actually, no. We can predict it in a small time. And actually, all our colleagues who spend in Europe or USA and try to, and usually they see the weather before they're coming out home, okay, to check the weather. It's very clear that the weather will be good, the prediction of the weather will be good actually within like 24 hours, maybe 48 hours. But later on, it will not be correct, and they corrected step by step. It is a complex system. It is very sensitive to initial condition, and this is what Lorenz said in 1963. Okay, it's what he said, the butterfly effect. The butterfly effect means if there is a butterfly change, like flapping the wings in China, it may disturb the weather in USA. Okay, how the small changes can make big disturbance later on with time. The different type for responses, as we know, there is a stable behavior when the system, when the output goes, becomes a steady state by after transient response. There is a periodic signal like sine, cosine, in like, or two points in the discrete form, or this what we said in the chaotic behavior. It is bounded between two values, and we cannot predict the value with time. And this, if we are talking about the relationship between X, the two variables, we have different relationship. It depends on the stable behavior, which is point attractor. This is what we said, periodic attractor, torus attractor, and this is the chaotic, which is the strange attractor. Strange attractor means the system, the behavior of the points between X and Y, which is two state variables of the system, changes with time. They cannot stop. They are moving all the time and will not repeat themselves at any time. There are several realizations for the chaotic system. Actually, in the beginning, okay, till like 2000, there are many realizations for the chaotic system based on the analog domain, using the op-amps and capacitors and resistors. And if you are talking about multi-scroll, which is more complex chaotic system, so you need more complicated op-amps, or many of them, and you should make sure that the system will work properly. And there are many challenges due to the tolerance, due to the temperature change. So working in the analog domain does not give us the full control of the chaotic system. So what we did in like last 15 years ago, we are working in digital domain. So we transform the differential equation into discrete format and apply this for the FPGA. It's very simple. It takes less area. This is the output of the oscilloscope. It gives you the same performance for the normal attractors. There are many known systems like Lorenz attractor, like modified Lorenz. This is by Professor Al-Wakil, and there are many also systems like this. The main, common that of the analog of the differential equation should be like third order minimum differential equation with nonlinear element. Okay, and these are samples of that chaotic system. There are more like what we see now. Okay, as long as the system can be simple, which is the simplest chaotic equation. Okay, it's very simple differential equation, third order, but B is the nonlinear term here and gives you the strange attractor shown below. Okay, if you are talking about Lorenz, we see how the performance, how the signal moves small step by step. This is X, Y, Z. Okay, this is the state variables. If X dot, Y dot, Z dot, it's very clear that the signal will move and try to increase. You assume that you can predict the signal, but actually after a few seconds now, it will not move by the same way. So it go right and left and nobody can control when it will go to the right side and the left side and so on. This is the same for the time domain. You can see here the time domain for the signals as well, how it can be it's different versus time. It can be grow up and grow down, and you cannot predict it for, as we said, for the long term, but you can predict short-term predictability. There is a short-term predictability, but you cannot predict it as a long term. So this is what for the chaotic system. Okay, for the chaotic system, we discussed the chaotic system in our project by different in different papers. We link the fractional order system, as we said here. Instead of doing integer order derivatives, we transform this into fractional order derivatives. We discuss several systems. We implement this in analog domain, in digital domain, and make and actually we use the memristor. We use the nonlinear elements using the memristor in our systems. So we published a good paper in this area and make a very good encryption applications, either in image encryption or speech encryption and steganography as well. And finally, we got a very good paper on the love modeling of using chaotic systems. Okay, how to model the love, the differential equation which models the love using using a fractional order and integer order differential equation which present chaotic systems. Thank you very much, Dr.
Thank you, Professor Ahmed. Love. So love is, after all, can be modeled as mathematics. So I believe now everyone knows why love is complicated, because it is mathematics after all. So Dr. Madian, can you please explain to us how love is mathematics?
So thank you, Dr. Lobna. Actually, this is one of the main, one of the studies that already has been done during this project. Is working with the tissue model has already give us some kind of why we didn't look behind the tissues. It's not always the hard parts that we have. We could look inside for the soft inside the spirit. So we tried to search for the most relations that already existing, and we tried to model. I shared something with you. This is one of the studies that already has been done during this project, and we tried to search more behind the tissues. What is inside us? Okay, the spirit. Okay, what is the kind of modeling for the relation like love? Okay, actually, this problem has been already handled multiple times, and there are multiple researchers that already working in a social level or an engineering level and try to model it in different ways to see what is the main parameter why someone could love or could like someone and hate another one. So without any reasons. So one of the main models that already has been implemented is a famous model of Romeo and Juliet. And as you see here, it's Romeo here, okay? And they say that love a triangle because Romeo here has two options. He has Juliet and Jennifer. So it's normal in the life, you know. Yeah. So and always Romeo try always to select this and leaving an open circuit between Juliet and Jennifer, so we can operate in something like that. So it's some kind of a very complex relation that already has a linear and nonlinear dynamics. So we tried to implement this relation. We searched a lot for some kind of equations that already try to realize this relation, and we found a lot of models that already has been implemented mathematically that already trying to describe what is the relation between Romeo and Juliet, and also Romeo and Jennifer. Okay, a lot of models of relations that has been implemented linearly. Actually, it has some kind of weighted inputs like A, B, C, D, and these weighted inputs already always control this relation. Okay. I hope we could find these weights inside us, but I don't know how to control it inside. But mathematically, we could try to put some kind of modeling for those relations. So we looked inside and we found, we tried to implement this part. So we get 3 different models as existing here inside this slide. We called it soft logistic implementation, hard, and a mix between them. So we tried to model that in 3 different ways to see how this nonlinearity could be implemented, what is controlling Romeo Y is going to Juliet or Jennifer or both of them. I don't know. That's okay. So it depends on the model. Okay. So this is one of the kind of implementations that already has been implemented, like soft nonlinearity. This is one of the models that was already had been studied. It depends, as you see here, the X parameter with J, this represented Juliet, with G is represented Jennifer, and both of them is representing Romeo feeling. Okay. So actually, I think maybe we could extend this for 3 or 4 more parameters, because but we have only triangle. We could say if we have a rectangle or something like that, so this could be extended more. Okay, but we try to work with this. So we try to study how those parameters could affect the relation between Romeo and the other two subjects, I would say subjects for this part, Juliet and Jennifer, by changing the different parameter and see how this affected in the relation of nonlinearity of dynamics for the function. This is for the integer soft nonlinearity, and as you see, changing this parameter, you could say that the relation between it could give us some kind of shifting, okay, in the behavior, as Dr. Radwan has just mentioned that in the chaotic. This is chaotic parameter, and another modeling for this so this problem was the hard nonlinearity, and the hard nonlinearity also it was already modeled also Romeo and Juliet feeling for Jennifer and Juliet for Romeo feeling, and we try to implement this function also and simulate with different parameters. It gives us another kind of relation that already may help us to see how the effect of changing the parameters could change the relation between Romeo and Juliet and Romeo and Jennifer. Okay, actually, in this relation, as we said in the first, we didn't get a dependent relation between Juliet and Jennifer. Okay, so the third line of triangle is not addressed here. So okay, if they know us, maybe this all would be put down because they will make a deal on Romeo. Okay, so a mixture between the soft and the hard model has been implemented just to see how this could be implemented, and we also simulated this. And as you see, changing the parameters of the equation, which models the Romeo relation with Jennifer and Juliet, give us a different behavior that already could lead us to describe how this relation could be controlled. All these relations has been done without taking into consideration the impact of memory and the order of the values that of experience. So for the 3 subjects of the study, okay, taking this into consideration, actually it could change a little bit the parameter. Actually, if Juliet knows that Romeo always is a playboy, so I think she would dump him. Okay, and the same for Jennifer. It could be something like that. Okay, so it has been already implemented here and described with different parameters, and we tried to generalize this on the different models that already existing in the hard and in the soft dynamics. So, and actually, we didn't stop at this point. As we say in NISC, we have already a high capability for digital implementation with different structure and architecture. So we went to the mixed soft and hard, and also we did the same study for the soft and hard. And here is already the presentation of signals. We try to extend this to be a hardware generator. Why I would implement something like that? It's a kind of chaotic generator that already depends on a relation that already has a high complexity, which could give us a benefit of a randomized thread or a randomized sequence that could be used in different communication system or different realization system. As you say, some of the encryption system already using a noise level to use it to generate the keys. So it's some kind of that could be used or to generate the keys or to generate something randomized for different functions. So we implemented those relations, as you say, Romeo, Juliet, and Jennifer, and the other parameter, and we already have designed that on FPGA. And actually, we did these blocks on one of the tools that already existing inside that FPGA kits, Arctic 7. And here was the simulation. This is not a real simulation. This is a realization inside the lab. This is taken from the oscilloscope after the implementation for the relation. And as you see, if we compare this with the simulated blocks for the soft and the hard cases, you will see that it already has a typical similarity with a little bit of error shifting. And this error shifting is not very high because we already have increased the resolution. So this could actually be a big advantage if we could implement this board inside Romeo, so we can control his feeling for Juliet and Jennifer. So just I will relay in parameter, I could shift him to Juliet or Jennifer. Actually, it's an interesting study that already has been leading a long time inside the center, and actually we have gained a lot of experience during this study. So this is one of the main problems existing in the life. I think Romeo always has to choose between Jennifer and between Juliet. So thank you.
I actually have to comment here. We understand now, after all, Romeo has a big heart as any man in life. So, and of course he died young. That's why he couldn't do the rectangle or maybe more.
Actually,
if he lived more,
he could guarantee living a long life once he got this open point inside the triangle. If he reserves this open point, he could live for a very long time. Yeah, but if you have this short between Juliet and Jennifer, Romeo will be dying for sure.
Yeah, actually, he will be killed, not kill himself. Thank you, Dr. Median, for this quite interesting.
I hope you enjoyed it. Okay.
Yeah, it's actually pretty much. I did enjoy. Okay.
We'll open the floor for the question at the end, maybe.
Yeah, we will.
Okay.
So, Dr. Radwan, so can you please summarize for us the project outcomes?
Okay. Thank you very much, Dr. Madian, for your description of this big paper. It takes more than 1 year in the preparation and publishing. Okay, let me share the screen. Okay. The outcome of this project can be summarized as follows. We discussed actually several items. We discussed the tissue modeling. We used the fractional bioimpedance models for 4 international papers, and demonstrates the possibility for extracting the parameters of the bioimpedance for many vegetables and fruits using the optimization technique and meat-heuristic, which is meat-heuristic optimization techniques for different. Actually, we discussed many optimization techniques and choose the best one of them. And this figure shows the sum of the experimental results, as we said. Okay, we used many experimental verification for the fractional calculus operator, and actually using the fractional in the encryption system, using SBox for speech encryption systems, and this is the oscilloscope results for the speech before and after the encryption. The above figure shows the speech itself, and the low one, it's almost uniform distribution after the encryption using the SBox and fractional order parameters we did. Actually, we also implement several emulator for the fractional order, and we published several. We published many literature review from this work. One of them for the cold impedance or the bioimpedance and its history. We published a literature survey of the fractional calculus as well from this project. We discussed the memristor and the 2-port network, how to design a memristor and to get different memristor behavior from 2-port network in different domains and using different structure, different fractional elements or integer elements, both of them. So we use them actually for chaotic systems and encryption as well, and see the effect of the memristor and the fractional order parameters, which gives more degrees of freedom for the encryption properties. And we made the simulation, circuit simulation as well. We introduced a fractional order chaotic system, and we use it in digital domain to make the encryption for speech and image encryption as well. And human behavior analysis, this is like the love paper we did in digital domain. And actually in the signal processing, we make like using the edge detection for biological tissues. And this is for we did this for the retina, and and the brain tumor as well, using the edge detection and how the fractional order filters versus the integer filters perform well. This is as well, and we discussed several fractional order applications like BV in power electronics applications, like fruits, emulators, and lots of applications that are related, oscillators, filters, inverse filters, implementation of all of these in different domains. We are proud that 2 of our REs have been, they finished their master thesis, Minna and Omar, as a part of this project. And actually, it's very good. We are lucky that we have very good resources in NESC and Nile University. Okay, everybody in the NESC, they learned lots in simulation tools like MATLAB, Cadence, and hardware like SP150, impedance analyzer, FPGAs, Elvis power, variable power supplies, and lots of experiments they did. And finally, we are lucky as well to publish more than 35 international papers, Scopus indexed from this project. And this has been done by our team. It's, as I said, we are lucky for our collaborators, for like Professor Kostas from Greece, Professor Luakil from Charger University, and lots of Dr. Fuda from USA, and many of our collaborators all over the world. Okay, and we are lucky for our RAs as well and professors in NESC. So that's it. Thank you.
Thank you, Dr. Radwan. Can you tell us how, I see lots of outcomes, mashallah. So can you tell us how many publications were, you know, as a sum, as a number, give us a number, how many publications?
Till yesterday, they are 35. Maybe it will become 37 by maybe a few weeks.
Okay, mashallah. Okay. 37 publications. I believe you have just made a record. Thank you so much, Dr. Radwan and Dr. Madian, for this very interesting talk. I'm sure our audience enjoyed it as much as I did. And now I believe we are ready for questions. So, okay, we have the first question from Abdurrahman Nusir. It was, okay, would your model be generalized to analyze different excitations for tissues or non-excited tissues with different status other than ideal tissue state? So, Dr. Madian, can you reply to this question? I will repeat the question for you. He was asking about, would your model be generalized? I believe he was mentioning, he didn't mention which model, but I think the circuit model, to analyze different excitations for tissue or non-excited tissues with different status other than ideal tissue state.
It's a very good question. Actually, as you see, this is an outcome for a research project. which already has been trying to model and trying to generalize a different models for different elements. But I think if we are going to generalize something like that, it would need more work and more investigation for the different cases and different parameters. And this could be need to be to extend this model with different elements to be generalized for this. But as you see, while my presentation for the tissue modeling, there was a lot of models that has been existing before, and those models doesn't exist just for fun. It has been existing because we have different cases that couldn't fit in one model. If they couldn't be fitted in one model, this problem could be solved. So this is why I wouldn't say that there is a generalization for something like that, but it may be need more work to get some kind of generic model that could fit with, I would say, most of the tissues, but not all the tissues, because I didn't believe that you could found one model for all the tissues. Okay.
Actually, I can add more for this, Dr. Madian. Actually, we discussed in this project how to make generalized model, okay? But as Dr. Madian said, you cannot find a general one model for all of them. We can, we tried to make a generalized model in with Minna thesis, okay? And I think it is not published yet, okay? We can discuss it in the future. This is one very good point, and we will discuss it sooner, inshallah, okay? So it is not easy to have one model for the human, for the fruits, for the vegetables, for the trees, because they have different structures, okay? The capacitive effect are different. So we discussed different models in this discussion, in this project, and we tried, but not implemented yet, a generalized one. And we will do it, inshallah. Thank you.
Inshallah, thank you, Dr. Ahmed and Dr. Madian and Dr. Adwan. I hope this answered your question, Abdurrahman. If you have any other question, you can either put it on chat or you just raise your hand to make a discussion if you like. So I have another question from Sarah. What is the difference between soft nonlinearity and hard nonlinearity in love modeling? So this is one part of the question, and the other part of the question, and how this affect the hardware implementation.
So it's a good question, Sarah. I have to share something, please.
Okay.
To get the difference between soft and hard nonlinearity, please look for this graph to the right. I don't know if you see it or not. Okay. if you see it
تمام شايفاه.
مش شايفاه؟ أنا عملت sharing for
لا شايفاه تمام.
Okay. Here is the difference between that hard non-linearity here. It means like the communication system. If you have a hard decision between 0 or 1, if you are transmitting something like 0 and 1, you have to decide if it's 0 and 1. So you have a hard threshold that already have defined if it's on or off. So this is existing by, we are using this function for the modeling of this relation. Okay. For soft, you have different levels. So those different levels has been implemented using a different function of logistic function that's represented as an x multiplied by 1 minus modulus of x. So both could be used for representation for the equations. It depends on the definition of the equation, okay? And the relation here is defined here in the soft. You will find that there is a more description for the relation for different points inside the field, but maybe in the hard, actually we have a defined points that already has been existing inside part. So if we are in between, you have to decide in which level you are going to. So the space here is already has to be defined on a specified points, but here in the software, you have already the flexibility to go through different points inside the space. I hope this answered your question, and maybe Dr. Adwan could add something if you want.
Thank you, Dr. Madian. No, it's fine. Actually, the difference as well, it's the hard represent, you know, the abrupt decision. If you are
share, do you want me to stop share, Doctor?
No, that's fine. Okay. It's a hard, you know, model which represent binary, as Dr. Mena said, -1 and 1, which represent the hard decision. Hard decisions means sometimes in our human behavior, sometimes we take hard decisions, but in other systems we use in a smooth behaviors or decisions. So this may represent a little bit about the two difference from the human behavior. Thank you.
Yeah, because it was definitely, Sarah, it was hard to choose between Juliet and Jennifer. So, okay, I hope this answered your question, Sarah. We have another question from our audience at the Facebook page. So I will read the question. They thank both of you for the nice presentation. And the question is, he thinks that we will work in a weak region to accommodate the low frequencies. If so, how could this affect the power consumption, as I expect for human tissues region is better? Okay.
Can you read it again?
Yes.
Okay, I will read it again. He say, my question, I think we will work in a weak region to accommodate the low frequencies. If so, how could this affect the power consumption? As I expect for human tissues, weak region is better.
It depends on what you are looking for.
Okay.
I think, because it depends on what you are looking for. If you're looking for just to get some general measurement about the human body or human tissues without looking for the internal definition for the system.
Okay. Dr. Median, are you with us?
So low frequency will be.
Dr. Median, we cannot hear you
yes.
Very good.
Yes, sorry. Is it okay now?
Yes.
Is it okay?
Yes.
Okay. So if you are looking for more details about the tissues from inside or working inside and so on, so I think in that case, you need to go for the high frequency. So I think it's more for the application. I know that most of our body is already working for the low frequency. Okay, most of the devices already could be defined as a low frequency, but in the investigation, we may need high frequency to penetrate to the inside tissues. And actually, most of the doctors already has those inside the biomedical devices. So to give them more. So it depends mainly on what you are looking for. I hope that I answered the question in the right way.
I hope our audience at Facebook just have a satisfying answer. And now we have another question. It is from Abdurrahman as well. He said, to clarify my question, he was wondering if you have plans in the future to generalize such a model for a single type of tissue that has different excitation such as muscles with different levels of tension. Yeah. Okay.
In that case, yes, yeah. I would say yes. We are already working on something like that to try to generalize for different conditions. Okay. Yeah, we are already trying to extend our work for that.
And actually, we are not working on human tissues. We are working on different kind of tissues.
No, you know, it's not allowed to work with the human tissues or living tissues without getting a lot of series of acceptance from a lot of committees, ethical committee, and a lot of things that already need to be defined already.
Okay. So we have a question from Muhammad Walid. He was asking, but this is a very wide scope question. Does fractional order system always give better results than integer order ones, or they may give the same or worse performance?
I will leave the floor for Dr. Alwan.
Yeah, exactly.
Okay. Thank you, Walid, for your question. Actually, the fractional order definition gives you extra degree of freedom. Okay. When you said d alpha by dt, so you have extra degree of freedom. This alpha change from 0 up to 2. So in the integer domain, it's equal 1, okay? So you have continuous region, okay, from 0 to 2. So if you are doing optimization for the experimental results, you can find the best parameter that match the best alpha that match your experimental work. Or by another way, if you are looking for the fraction, for the integer, for the capacitor we are working in the lab, it is not integer capacitor, because if it is integer capacitor, it will be like lossless. Okay, so it will store all the power, which is not true. So it is not a fraction. It is not integer capacitor. But if you are measure the response of the actual capacitor we are working on versus frequency and magnitude and phase, and then you model this performance using the best for the fractional order, you can find the best alpha, which may be like 0.95, 0.98, which means that you have better option and extra degree of freedom to model the actual parameter or the actual elements we are working, and assume it is linear, it is integer, and it is not, okay? And actually, okay, I would like to share, Dr. Median, we have a very good video for the cancer. Do you have this video for the cancer, the bioimpedance? Okay,
I didn't get it now.
For the muscle, it is not our work, but actually it is very good point from Abdurrahman that to discuss the how the bioimpedance can affect the muscle and the cancer for the human body. And actually there is a very good device that have been already existing now, and try to get to predict the cancer okay, of the human body using the bioimpedance model. Okay, we can share it with you, okay, later on, if you can send us your email.
If you send your email on the chat, I think we could forward this for you.
Okay.
Okay, we have another question from Shahinda. She said, Dr. Median said that we can't control feelings in reality, but we can control it using mathematics. Can you explain how to control it?
Actually, it's a very interesting point, as I said, but actually controlling a human is not applicable. But in mathematics, if we are controlling the parameter inside the equation, this could control mainly the behavior of the function, and the behavior of the function is tending to one of the triangle points, like in case of Juliet and Jennifer, it could be shifting towards Juliet or Jennifer based on the parameters that we are defining in the initial conditions and the values of the parameters that we are taking. Okay, so controlling those parameters could generate a different values in each trial based on the constants that we are using. Okay, this is in mathematics. But in the life, maybe the behavior of relation between humans could change this. This could be the parameters, okay?
Thank you, Dr. Median. I think people are very much interested about our interpretation for love, so...
Actually, it was a trial that took us a long time to get to the outside world. And it started mainly by modeling, and then we extended why we didn't use it in an application that need some kind of random generation or chaotic behavior implementation. So it's always something like that. As you see, most of the optimization technique is already getting from the nature. Okay, we have ant-colonies that are coming from ant. We have a bee optimization techniques. So genetic. So we tried also to implement something like that, is to get some kind of the relation between humans, and they try to use it and in a function that could be a benefit both.
Okay, thank you, Dr. Median. We have another question from Summer. If we implement tissue modeling using machine learning or CNN, would it be better than analog implementation or would it be worse?
Sorry, again? Is this for me or?
You or Dr. Radwan, what, I will repeat the question. She was saying if we implement tissue modeling using machine learning or CNN, would it be better than analog implementation or worse?
Okay, actually we implement the tissue modeling, the bioimpedance by different ways, digitally or analog, but we didn't discuss the machine learning till now. It's a very interesting point, and we will try to discuss this, inshallah, with our research center in CIS in Nile University. We have a very good team in machine learning and big data, and it's a very good point to discuss it with them. Thank you very much.
Thank you so much, Dr. Radwan. So I see no more question on the chat.
So I would like to say hi for my friends and my colleague, Panioti and Stavrola, okay, from Greece. So I think we all of us send you regards and thanks for attending this session.
Hello, Professor Madian. Thank you. Thank you for the great presentation, both of you.
Oh, thank you. You are welcome.
Hello from me. I'm very happy to see you again.
Hello. Everything is okay?
Sorry?
Not as much the same, but we hope that now we're vaccinated.
We hope so. We hope so.
Thank you all. And at the end, I would like to thank the STDF for supporting this project. I would like to thank all our colleagues who participated in this work. Okay, Dr. Madian, Dr. Lubna, all RAs. There are many who participated in this work actually, and everyone. I would like to thank them all. I would like to thank Nile University for supporting the project and offer the equipments, the space, and everything, and for the publishing of the 35 or more papers during this project. Thank you very much.
Thank you, Dr. Radwan, and thank you, Dr. Madian. I would like to give a special thanks to NU Research Office and NEST Research Center for co-organizing this session. And I think I have told you at the start, this is the second video of our series. So wait for us, we will come back with more interesting topics and more dissemination for our research projects. And thank you. I would like to also thank our audience at the Facebook page. I hope you all enjoyed the session. And thank you, Professor Radwan, and thank you, Professor Madian, for this very, very interesting session. And have a nice rest of the day. Thank you.
And have a nice weekend for all of you.
Thank you.
Okay. Thank you very much.
Goodbye.
Thank you.
And please, Stavrola, say hi to Professor Costas.
Of course, of course.
Send him our greetings.
Yeah, he took his vaccine now, so he couldn't be here.
Yeah. I hope he's fine. He will be fine soon, inshallah.
Thank you.
Thank you.
We will contact him, inshallah. Okay. Thank you.
Okay, goodbye.
Bye.
Bye.
Thank you. Thank you all. Bye-bye.
Bye-bye.